today we have been talking about joy, we have been talking about thinking. That's the motto that we have, enjoy thinking. But I wanted to focus a little more into, okay, if thinking is the goal, is our North Star to get joy, what are the blockers? What are the obstacles? And probably we all can think of several obstacles, and some obstacles might be more relevant for some of you, and some obstacles might just have been overcome by you in the past. But when we were discussing this with Rob and with the team on the presentation, they gave me this metaphor, this sentence in English, the pebbles in your shoes, right? So we're going to explore some of these pebbles. What is a successful math class? The ones that have heard me before know that I always start with this question. And I want you to reflect for like 10 seconds, because since we are 5 minutes late and I want you to think later, I'm just going to skip this real quick. Think for like 5 seconds. What is success to you? Probably, my beard is, okay. Probably you're now thinking about joy, about thinking, about engagement, about kids collaborating. All those words come up when you ask this question. I love asking this question to pre-service teachers at the university, but also to kids. What is success for you in math? Because then you can sense the temperature of the room. If the audience, you're doing this in your district to some of your colleagues or some of your staff, your teachers, and you ask these questions, and the answer is that the kids are quiet and listening to me for a full hour. I don't know if that would be priority one to me to call it a successful class. Or if they say, no, it's when the kids give all the answers right. Is that success? So this question is a good thermometer to sense how the audience feels about math. To me, there are many definitions, but the one that we love here is the one that includes the word thinking by Tracy Zager, the prologue in Building Thinking Classrooms by Peter Liljedahl. We had the chance to collaborate with him in the translation to the Spanish version of it. So we had to work also with the prologue. And we love this quote from Tracy. Success means getting more students thinking for longer amounts of time. But some teachers, when they hear us talking about thinking, or when we see the activities that Dr. Milou used today, they think, oh, this is a nice activity from time to time, right? Like an anecdote, we're gonna do, I was once in a classroom and the teacher was doing one of these tasks, and at the end, he said, okay, now we're gonna do math. Like, wasn't it math already? Why do we separate these fun games, activities with numbers, like the ones that we just did, from the actual standards alignment, going to the algorithm? Can we mix that? That's what Tracy Zager is saying. We have to allow the kids to think for longer amounts of time. It's not just a spark. Thinking should be a state of mind in your classroom. But thinking includes the teacher as well, right? So when we read Building Thinking Classrooms, we think, oh, okay, the kids are going to think more. But what about us as teachers, right? Building.
I'm sorry.
Yeah, I'm not Madonna, so I don't know how to wear this.
It's fine. I'm sorry. I just need a little louder for the back.
How is it going? Good? Yes?
Better? Thank you.
I feel powerful. Okay. Now, the pebbles in our shoes. What is preventing us from thinking? I'm going to explore 4 with you today, but probably we can have many more. And Rob, who was sharing with me this metaphor of the pebbles in our shoes, he said, you have to be very intentional in calling them pebbles and not rocks in your shoes, right? State testing, that is not a pebble in your shoe. That is a rock, a massive rock in your shoe. We cannot get rid of that big rock in a second, right? These pebbles are like little things, little actions that are preventing us or our children from thinking, and that we can rather easily remove, or at least with little actions. Okay, these are the 4 that we're going to explore today. The first one is, I am not a math person. And that affects the kids and affects us as teachers, right? Both. And also society, parents, families is another rock, it's not a pebble, so we're not exploring families' relationships today. Number 2, there is a ton of research. The Common Core says that, the standards in New Jersey say that, that mathematical practice is a lot of research, a lot of intention in solving problems. But do we all here agree on what is a problem? Because if when I say we should be solving problems, your interpretation of what is a problem is different from mine, then maybe we're not talking about the same thing, right? And especially speaking in English, you probably can see that I am not from the United States, I'm from Barcelona, as I said. So in English, since you say word problems, right, that is lowering a lot of significance to a lot of meaning to the word problems, that really makes some teachers think that when they do word problems, that's all they have to do when it comes to solve problems. But the word problem goes beyond word problems. Yes, we're going to see that. 3, the mathematical horizon. Where are we going? Where are we coming from? I am tired of teachers thinking, and I was one of them 10 years ago when I started in this profession, saying to me, oh, but this is not on my grade. This is, no, oh no, I don't do fractions. The fractions are not, I only teach first and second grade, I don't do fractions. Okay, yes, you don't do fractions, but what seeds are you planting that are gonna later on help and contribute to the understanding of fractions? And the other way around, high school teachers don't tell me, no, how to count, how to subtract, that's too easy, I don't deal with that. You have to know where we're coming from, because then we have stragglers, and how do you help them if you don't know what are the steps where we're coming from? So the math horizon will be also important. And last but not least, what's our role in all this, right? Are we guides? Are we just talking in front of the kids and giving a message and then leaving? How do we assess that the message is getting there, etc.? Those are the pebbles, and we are going to explore them one by one. Pebble number 1. I am not a math person. So if you saw me in some of this maybe the last year, I've been adding this to my conferences because I saw this at the NCTM and I love this exercise. This is my math identity graph. Still empty, so it's a slow reveal graph as Rob did before. What do you see? Don't worry, you can just speak up. What do you see? An empty what? 2 lines, 2 number lines, 2 axes, right? We're going to talk about the number line later. What do they represent? What do you think? The vertical axis, math identity. Someone here said interest in math, somehow related, yes? Some people think it's how good you are at math. No, you can be good or not good, but that's not directly translated into your math identity. But it's related, but it's somehow connected. What else do you see? How do you feel about your ability to do math? Feel confident? No, right? And what's the horizontal axis? Time, right? So this is me. Questions? What do you notice? What do you wonder? And I know you probably are not that interested in my private life for now. Maybe at the end of the presentation you're like, wow, what happened here? But let's fake it until we make it. What questions do you have? Yes?
I think we probably have the same question.
Same question?
Why did it zip?
What do you mean by zip? I like that. What do you mean?
It went down.
Why? So you like drama. What
It's true.
what brought me to the dark side, you mean?
Yes.
Yeah, that is an interesting question. So that, right? What's that slope down the hill? That's a good question. I'm going to answer later. Other questions? What was that? Okay, the bright side, right? What took you out of that dark side? Okay, what else? Yes. What grade was I teaching? Okay. What part of this, and now it's a guess my age type of game, what part of this do you think it's me teaching? And what part is me being a student? Right?
I bet you the bottom is you being a student, right?
Oh, you didn't meet my third graders. No, just kidding. But so yeah, there's part of this that is my student life and part of this that is my teacher life. It's my student life today is still longer than actually I'm finishing my PhD, so it's been a never-ending story, my student life. But okay, so let's talk about a few spots in here. while I do this, you can start thinking on how is your math identity looking like, right? And I don't recommend you do this activity with first graders or second graders, maybe it's too early. But from third grade on, this is a great activity to do the first day in class and the last day in class and compare. How did it change? What happened this year? Did we go up? Probably we went up and down. If we zoomed in this, which is summarizing some years, probably we would see some ups and downs. But, okay, what happened here? So this is, I'm going to try to point with the pointer here. This is me doing well and having a positive mindset around math in elementary and kinder and elementary. Actually, I intentionally started the graph in a positive side because I think that when we just are born, we don't have any prejudice or like anything against math. It's what happens to us, it's our story, what brings us up or down. And here, I had like a boost at the beginning of high school. Like, okay, I'm seeing like more serious math. I was rather good at the math class. So I was like, yeah, this is going great. But then this flat zone at the top of the mountain, which is, yeah, okay, I can solve problems that I am being asked in high school, later high school, but I'm not getting more and more interest. Actually, it was the ground for what was happening next, which is the drama side, which is starting at the university. And this is the key fact that for me, it happens to anyone, right? At some point, if you're only relying on memory will fail you. Sooner or later, it will fail you. For me, it was college. I was getting A's in elementary and high school, but then middle and high school. But then when I get to college, I see that all that I thought that I knew about math was just there because I was good at memorizing. But then when you try to memorize calculus or algebra 1, or, well, algebra 1 is in high school for you, but algebra at the university in college, then everything started to fall apart. And I started to think I'm not that good at math, I don't like it, I don't want to do this. I was trying to become an engineer and I didn't like it at all, right? But then at some point I discover and I decide against my parents' will that I wanted to become a teacher, right? After all these years, now you want to be a teacher. That's my dad. So yeah. You could be an engineer, you could be rich, and you want to be a teacher. And this is in Spain, which is another situation, but I think that the US reaction would be the similar. And lucky for the US and for Spain, teachers are not like or are not seen as the top of the food chain, right? When it comes to jobs. Well, an engineer, or why not a doctor or a lawyer, right? Those are the professions that we typically think of when we think of successful people. Why not a teacher? And I was very passionate about it. I started teaching, and then I saw the light, right? I regained this joy for math because I saw that math education was not what I had been taught as a student, right? So this bright side is me as a teacher and going up, and I don't know where, but sky is the limit. Now, who relates with this shape? Like going up slightly, elementary, and then at some point, maybe earlier or later, maybe it was geometry 1, algebra 1, calculus, whatever, down to hell. Who relates with that shape? Okay, most of us, right? Who has never been to the dark side? Xavi over there, one of our team members, is a very good high school teacher. Yes? Okay, but there's a certain value in knowing the dark side because most of our kids might visit that dark side at some point. And then how can we help them go out of that dark side, right? I don't think that we have to prevent people that much from going up and down. It's like, okay, what do we do when they are down there? Let's see, what can we do? What's your math identity graph? I think that as we continue with the presentation, you can maybe draw yours, and that can be a good story to share with your table mates when we go to some activities. But for now, let's move on. I don't like slides with a lot of text, but I needed to share with you this quote by Chestnut that I love. It says, "Many people seem to believe that with respect to math, the world consists of two groups, those who are math people and those who are not math people. Underlying the very idea of a math person, that's what we're talking about, is the more fundamental notion that doing math required some sort of innate quality." This is a myth. with suitable effort and strategies as well as appropriate instructional guidance, this is us, every school student can be proficient in math. Every school student can win the Fields Medal, which is the Nobel Prize for math. Probably not. That needs some spark or some talent. Okay, can give you that. But be successful at least in math in school, for sure. And if you caught yourself sometimes, like me, thinking this kid is not a math person, or even yourself, fight against this myth. This is not true. There is no scientific evidence that supports the notion of being or not a math person. So if you catch yourself sometimes thinking, oh, this kid is not good with numbers, maybe this kid has dyscalculia, maybe he has some difficulty, okay, but there is no scientific evidence that supports the notion of not being good at math, because math is more than numbers. Maybe the kid has struggles with the numbers, but what about geometry? What about algebraic thinking? What about measurement, right? Some quotes that I invite you to read if you are these kind of people that want to go deeper and deeper and read the references. Did you watch Inside Out 2 already? Yes. Who watched it? Yes. If you didn't, it's a great movie. And you know this character? Anyone remembers this character? Anxiety. I love how my talk is complemented by, or is complementary to what Eric said. Because joy has two main enemies. One is boredom, that I think that his keynote really addressed, fighting against boredom. But there is also another big enemy when we talk about joy, and this is anxiety, right? The number one feeling preventing us students to feel joy is this anxiety, and anxiety, that's why it's related to math identity, is not about the skill that you have, it's more about how you feel, right? This feeling around math. And at some point, since math is, and problem solving is challenging, at some point we will feel this kind of anxiety. It's not about preventing us from feeling this, it's what we do then with this kind of feelings. Our minds and bodies freeze, right? There is a paper that investigated the neuroscience part of the brain that triggers when we see math, and of course not everyone, but some kids, some people triggered the same part of their brain as if they saw a spider or a snake. Can you imagine that you are like, okay, there is a natural biological reason to be scared of a snake, it's poisonous, okay, or a spider, and math? How did we arrive there? And you can see that sometimes in kids that are 3 or 4 years old, what is going on? What happens? And we, as teachers and parents, are responsible for that, right? And then, where is this rooted, right? And this is from a conference that I saw Vanessa Bakarian, the math guru, that I recommend you follow her in social media. She's always publishing ideas and activities, and she's now fighting a lot against anxiety. And she roots that in the fear of failure, right? So why don't we, there is a good thing about math as you start seeing what's going on on the screen. And I love this because any mathematician that you talk to will tell you this. The great thing about math is that when you talk to math, math talks back to you. And that doesn't happen often in the rest of disciplines or subjects that we teach in school. You ask math if something makes sense, and math talks back to you and says yes or no, right? So how can a discipline that behaves this way, that talks to you, how can that be scary, right? I would rather be scared of an essay that I don't know if it's right or wrong until the teacher reads it and says it's right or it's wrong, than a thing that I can check on my own. There is no risk in that. I can make a mistake, that's part of math. I can check, recheck, rethink. Why are we not experiencing this joy, right? What do you see? I'm gonna stop talking in a second. Can you imagine me in Spanish? I'm like, You're lucky that I'm doing this in English and it's harder. Okay, what do you see? Combinations of? 5. 5 what? 5 dots? Yes. So combinations of 5. Any type of combination? The sum? But for instance, 1 plus 1 plus 1 plus 1 plus 1, is that there? Okay, in 2 addends, so different combinations of 5s in 2 addends. So would it be reasonable if I told you that this is 5 in 6 different ways? Yes? This is from one of our workshops I know at in kindergarten. We are obsessed. If you ask me, number one priority in pre-KK, we are obsessed that every kid lives the year knowing that numbers at least 1 to 10 can be decomposed in many different ways, right? Why is this important? And this, here again, we are planting seeds. Why is this important? Because imagine that I want to do 42 minus 5. I know this is not kindergarten anymore, but I'm trying to connect these two things. What can I do? Why am I focusing in this particular representation of 5? Yes? So seeing the 5 as 2 and 3 allows me to comfortably jump from 42 in my mind, right, mental math, and say, okay, that's 40, and then 3 more, or 3 less in this case. So here, if you see 5 in any form that is a 5 actually, you are having another help when it comes to, for instance, subtract or add. But that comes with the notion of seeing, for instance, number 5 in any different form, right? So 5 is not a thing that is living there outside of you, that is like, okay, this is 5, it's an entity, a number that you cannot touch or that you can, and it's there. That's what gives this layer of math connected to intelligence. Like if you're good at math, you're intelligent. If you're not good at math, you're not intelligent, that which is terrible for math and for intelligence, because there's there is no needed connection. But how about seeing 5 in all these ways? And you can count them. If you don't know how to add, can you count here the dots and realize, even without knowing how to add, that those are 5s? So again, this is talking to us somehow, and we can go back one step and try to build again. One of the sources for fear is that math is very cumulative, right? So when a stone in the building fails, everything falls apart, which happened to me in my story, right? When everything failed, when my memory failed, I started to feel bad about math. So it's always about rooting things and trying to build a castle as solid as possible. What about this? And I don't want to hear anyone thinking, no, negative numbers, I don't do negative numbers in elementary. I know you don't, but where are we going with negative numbers? What is the answer? 5 minus minus 3. 8. Why? Because negative and negative makes a positive. But what if I tell you that I am from Mars and I just landed on Earth and I don't understand what you mean by minus and minus, it's a plus? Who decided that? Why? Convince me. That's my favorite sentence to say to the kids. Convince me. I was with a kinder class last year because it was September, and this little kid, we were showing some pictures of like statues, and there was this beautiful picture of 4 statues. So I asked the kid, how many? How many people on the screen? And the kid says, it's 4. I'm like, why? It's 4. Like, can you convince me? And the kid is like super confused, like, is this the math expert that was going to help the teacher? And I'm like, no, convince me. Why do you think this is 4? I think it's 3. Kindergarten kid. The kid says, can I come to the screen? And I say, yeah, be my guest, come. The kid comes and does 1, 2, 3, 4. It's 4. And now I'm convinced. My favorite question all the time is, why? Convince me. Why? And that gives you time to think as a teacher, right? As the kid is trying to. So here, if I ask you why, I'm not asking you to prove it, but how many people would feel confident convincing me that this needs to be plus? Okay, just a few. 3, 4. Let's see if your explanation matches mine. What are these groups? Now we have positive and negative chips. You see, like, okay, 0 pairs. What do you mean by 0 pairs? A positive and a negative, what? They cancel? Okay, so what do you see here 4 times? Like with the cards. Is it 5 in 4 different ways? Can we agree that the first one is 5? Yeah, 5 positive. Can we agree that the second one is 5 too? Is another way of seeing a 5? Do we all agree? Yeah. Can we see all the 5s? Can you imagine any different 5 that you want? here? Like, can you imagine a 95 positive chips and then 90 negative chips? Would that work and be a 5? So 5, and this is a very powerful idea, has infinite forms. And that's starting to make sense compared to the cards that we were using before. These are 5s. So when I want to do 5 minus 3, I just removed 3, and you convinced me that the answer needs to be 2. But if I want to remove 3 of the negative ones, I prefer this form of a 5. You see why? Because then, if I want to remove, remember that the minus is remove. We just did that. So I want to remove 3 negatives. I need this one. I remove 3 negatives. What's the answer? 8. It needs to be 8. It makes sense. I talk to math. Math talks back. Yeah, this makes sense. Great. We're getting along with math, right? Do you see, I don't know, I mean, the few hands that raised up probably knew this, but do you see how powerful this idea is connected to what we did in kinder? And trying to make sense so that the kid doesn't think, oh, it's minus times minus equals plus just because the teacher said so, just because it's a recipe that I am following. No. Are you understanding it? Why is it working? Is it talking back to you? Is this a pattern that you see? And this is not magic. Some kids are not yet getting it just with this. So, but imagine having this in 7th grade or in 6th grade with manipulatives. Can you envision how the kid would understand much better why minus times minus equals 8? But Albert, are you meaning that I am not telling the kids the tricks, the little tricks like minus plus or minus times minus? You can tell them that, but later. It's even more. They will discover those. And those tricks are okay, like the algorithm, afterwards. In Spanish, we have a saying, don't start the house by the roof. Don't start the house by the roof. Start with the pillars. Start with the ground, the foundation. Okay. Another little example, probably this is more well known. How would you calculate this multiplication of fractions? Instead of calculate, I prefer draw, represent, understand. So I would do 3/4. Would you agree this is 3/4? And then I would multiply times 1/5. Would you agree this is 1/5? But then when I overlap those two representations, what are the green shaded ones? The blue plus the yellow, or the blue times the blue times the yellow. You see what happened? Are you envisioning this overlap? And see why it needs to be 3/20? And then we can discover that, oh, but we could have multiplied numerators and denominators and it works. Yes, great observation, but afterwards. First, we have to build understanding. And that comes with thinking and with what do you notice, what do you wonder. So these lessons or this kind of math at the beginning feels slower, but it travels much farther. Probably we all know this right here. Who knew this example, like how to multiply fractions? Yes? Makes sense?
One of my students said, this is math, not art.
Well, math, that's a good conversation to have. There is many mathematicians that feel that math is art, is one form of art, right? The most pure way of trying to see the world. So we could have a great conversation around that topic. All right, so this is just two isolated examples on how to build understanding. Do you see that if you do this, many more kids will get on board and feel less anxious about arbitrary things that the teacher is throwing at them? Is it magic? No. Some of the kids will feel anxious. Yes. Some of the kids will fail. Yes. But it works much better. All right. And I love this quote, and this will remove the first pebble of our shoe. Can you imagine attending an art class where the only thing you were taught was how to paint a fence or a wall, where no one ever showed to you the works of great painters? Would you like this art class? I doubt it. Obviously, it sounds ridiculous. Yet, that's how mathematics is taught, and as a result, to many people, it's the equivalent of watching paint dry on a fence. Math needs to be about aha moments, as Dr. Milou was also pointing. This is from a wonderful book called Love and Math by Edward Frenkel, who actually is American, and this is an awesome book. Or maybe he's British, no, I'm not sure. Anyway, pebble number 1 removed, we all agree? Of course, in 10 minutes or 15 minutes that we have been talking, maybe you still feel the pebble, but now we have tools to at least remove our shoe and take it out. Alrighty. Pebble number 2. What is a problem? And I'm asking you, what is a problem? If you have seen me before, you probably know the next slide. But if you don't, what is a problem? There is no right or wrong answer. So let me know your thoughts. What is a problem? Something that makes you think. Yes, okay. I like that. What else?
Something you're curious about.
Something you're curious about, because if not, it's not worth investigating, right? So we need some curiosity to spark. What else? Something you struggle with. So it needs to be kind of somehow difficult, right?
Something that needs a solution.
Something that needs a solution. Yes? I love all the definitions you're giving me. I think they all complement. We need a solution, we need a strategy, right? And therefore we have to struggle a little bit until we make sense. But to struggle, you need some curiosity. That's the fuel you need to keep thinking, right? If you're not even interested, it's hard that you have this productive struggle. So again, I'm going to building thinking classrooms because I really love this. This should be a tattoo. I don't have tattoos, but this could be. Problem solving is what we do when we don't know what to do. So if you know, then it's not a problem to you. And then it might be interesting in the math class. I don't say the opposite. An exercise might be interesting to practice, but don't call it problem. Because the moment you call it problem, you are killing all these ideas around problem solving, right? Of course, this state of not knowing lasts for a while and then you figure it out, right? That's the, or not, as the Collatz conjecture that has been around for ages and no mathematician has ever solved it, so it's a problem. Okay, so having this in mind, I wanted to do a vote to pretend that this is a democratic session, but it is not. So I'm gonna move on because some of these activities are too similar to the ones that Dr. Milu shared. So this one, I'm gonna skip it. I'm gonna do this one. Look at these windows and you can talk to your partners. I'm gonna give you like 1 minute because I don't want you to think about the problem yet. Just what do you notice and what do you wonder? These are windows on sale in a shop that they sell windows. What do you notice and what do you wonder?
I noticed that different windows have different prices.
Okay, different windows, different prices.
I know. I wonder the price per unit.
Okay, what's the price per unit? And by unit you mean?
Little square.
The little square. Okay. What else?
Different quadrilaterals.
Okay, now we're making a more explicit connection to math here. Different quadrilaterals. So we're talking about rectangles in this case. Are they all rectangles?
Yes.
I hear many yeses and some no's. Is a square a quadrilateral? Is a square a rectangle? Yes, it is. A very special type of rectangle. It's so special that it has a name, but still a rectangle. Because what's the definition of a rectangle? 4 right angles, right? So a square must be. Okay, so here I have some questions to you. You can pick the question. I mean, I would go in order, but be my guest. Choose a question that you are engaged with in your table. I added a last dot there that says etc. So you can make your own questions and bring me an investigation on these windows, okay? Some of the questions that you can explore with your table are, how is the price of a window calculated? You already said that. Can you have 2 different windows with the same price? What is the cheapest window you can buy that uses, and you can set there a number of tiles. How many different rectangular windows can you create using 12? Which one is the cheapest and the most expensive? What about 13 tiles? And so on and so forth. So pick one of these questions and start thinking. If we had the space, if I was in a classroom, to do more, like to honor better building thinking classrooms, I would have vertical surfaces on the walls and do random groups. But I think that it will be a mess now to randomize you. I think that you probably don't know everyone on your table, right? Anyone knows everyone in their table? Now, you're not going to confess, right? So it's kind of random. Collaborate, think. You can split or work together, the 8 of you. I'm going to give you 5 minutes. Investigate. Which questions are interesting to you? Go for them and bring me some answers. Let's go. Okay. I know you are still investigating. There is the joy again, right? And you're now probably annoyed that I stop you. It's good. When your kids prefer that you just be quiet and they can think more, that's perfect. That's the state of mind you want in your class. But it's true that we have a limited time, so I have to cut it here and have some conversations. Okay, so I'm gonna randomly pick a table and ask what were you investigating, share with us. So maybe I'm coming to this table over here, if you don't mind. What were you investigating? What did you conclude? What question caught your eye?
We were trying to figure out the price, how much.
I'm going to revoice, don't worry.
We wanted to try to figure out how we get the price of the windows.
Okay, so the first question. They were interested in the first question, right?
And we were tackling, like, it has something to do with area or perimeter?
Okay, is it area or it's perimeter, right?
Square units.
Square units with the tiles that we were discussing here.
No conclusion yet.
No conclusion yet. But it's okay. But what's your investigation going? What are you doing with that? So do you think that area is involved in the price?
It doesn't seem likely.
Let's ask ourselves this. The bigger the area, the bigger the price. Is that true? Is that a true or a lie in this case?
That is true.
That is.
So that is a lead, promising lead. The bigger the area, the bigger the price. But not only the area is important, right? And you said another word.
Perimeter.
Perimeter, that probably is involved here. I don't know if you see it, but it's a glass windows with frames. So probably the frame is involved. Okay, anybody or another table that was investigating exactly the same and have a little more of a conclusion on the price?
We noticed that the square was $10 more than the rectangle.
Okay, so you went for the ones that have a closer price.
Yeah, so we
140 and 150.
Yep, and so we thought right away that the piece with no frame is $10
The piece with no frame is $10. What makes you say that?
because it's $10 more than the 141, and the 140 doesn't have any with no frame.
Okay, so you see how, and that's algebraic thinking at its best. We compare two equations. In this case, it's just a picture, not an equation, but it could be an equation. And we are comparing the two that are closer. And she's saying 140 and 150 are close enough, but the only difference between 140 and 150 frame is the middle square that has no frame. And that, therefore, my conclusion, probably right, but we don't know yet, is that part is worth $10. Okay, and that would mean that every side of this square as a frame is, how much would a wooden stick for the frame cost?
With one frame or two?
One segment.
$15.
15 with the glass and then one frame. So
Yeah.
10 plus 5.
And then the corner pieces would be 20.
And the corner piece would be 20 because it's the full square. 10 plus 2 segments of 5. 10, 5 and 5 is 20. Let's see, thank you, that was a great investigation. I'm gonna show there with the pointer. Okay, let's see. I'm gonna repeat real quick here. So, we see that this corner, I'm looking only at the frame. This corner is this corner. And this corner is this corner. And then this corner is this corner. And then this corner is this corner, right? And then we have these middle segments here that can be related to these 4 and 4. So the frame is the same. Actually, in other words, the perimeter is the same, which is 12. But the area is not the same. Area 9 and area 8. Therefore, their conclusion was this difference in the area must explain the difference in the price. Right? It's a fair conclusion, isn't it? Okay. Now, why did I give you 3 windows and not only 2? To check. Can we check if our conjecture, for now conjecture, is true with the last window? Let's do it together. What's the area of the big window here? 24? Okay, 24 times 10? 240 of glass. And then the wood. What's the perimeter? $5, and how long it is? 20. 20 times 5? 100 plus 240? 340? Very good. We can give an applause to that table who figured it out. Yes. Yes. Now, if your table was still figuring it, does this make sense? Do you think that that was your line of thought that you were heading to? Yes, probably with a little more time. I'm sorry that I cut it. This is a terrible teaching practice, but we have to. Okay, let's explore a few more questions just like this, and we move on. Can you have 2 different windows with the same price? Yeah? Can you give me an example?
Like a different array.
Different array, but with the same price? Could you?
Yeah.
Such as? Do you have an example?
Well, like it would just look different. So
It will look different, yes.
2 by 4 would be, it would be the same perimeter.
2 by 4?
But it would be like this.
2 by 4 is one of the windows, and the other one? No, I don't know. Honestly, and this is a risky movement as a teacher, to be honest. I typically bring some questions, not every day, because this is exhausting, but I try to bring to the classroom some questions. I remember talking to Mike Flynn about this, and he was like, oh, I never thought about this, and this is interesting, and it's not my approach. Bring some questions to the classroom that you never thought of. In general, 99% of what you bring should have been thought before, because that's when you see all the where you're going, etc. Yes, you need to have a plan, yes. But from time to time, put a question that you don't know. So you genuinely can engage. I know the answer of all of them, but for the second question, I honestly don't know if it's possible. Probably it is. I have a guess, but I don't know the answer. I don't know if there's one answer or more than one, right? So that's a question that I leave you to investigate over lunch if you want, okay? I honestly don't know the answer, but my gut say that it's a yes. Sorry. What is the cheapest window you can buy that uses? Of course, the cheapest window is 1, but then we could add some constraints to that sentence and say that uses 5 squares. What is the cheapest window that uses 5 squares? What is the cheapest one that uses? Let's think about the 9 here, for instance. Yes? With 9 tiles, what is the cheapest window you can make? A square? Why is that? What do you know that allows you to say this so confidently?
It has the smallest perimeter.
Okay. If I say, did you hear her? She said, because it has the smallest perimeter. That's very, very interesting. So, given the area, 9, imagine all the options that you could have with 9. For instance, 1 times 9 would be a very long window, like that one, for instance, right? That would be 9 times 1. But you also could have 3 times 3, yes? Both in glass cost the same, 90. But then what about the frame? What about the perimeter? Right? The perimeter of this square is what? 3, 3, 3, and 3, which is 12, right? What's the perimeter of the 1 times 9? 20. Would it be cheaper or more expensive? More expensive. And this is a powerful idea in 4th, 5th grade. Area and perimeter have an unstable relationship, right? It's not always true that the more perimeter, the more area, or the more area, the more perimeter. Sometimes it messes with you. Given an area, the smallest perimeter is the square. And that's related to given a volume, the smallest perimeter would be a cube, right? The smallest amount of surfaces. And it relates to what do you do when you're cold? You try to minimize your perimeter. You try to become a square or a sphere. What do you do when you're hot? You try to have a longer perimeter because you want more surface on the exterior so you can get rid of that heat, right? This is a wonderful connection. Okay, and then these questions here, how many different can you create using 12? You can think now of factors, and that's a spoiler alert for you. I wouldn't tell that to the kids, but 1 times 12, 2 times 6, 3 times 4, and the vertical ones. And all those windows give you the factors of 12. So finding the factors of a given number is no longer what I used to do, which was like put their line and try to, that can be like the last step. But before that, are we understanding what are the factors of a number? Yes, the sides of the windows. What would happen with 13? How many windows could I create with 13 tiles? Only one. Well, the sleeping, my kids say the one that is sleeping and the one that is awake, but it's the same one, right? So why? What is happening with 13? Why is 13 different from 12? It is a prime number. So suddenly the definition of what is a prime number is no longer only the number that has only one on itself as factors. That can be the last step of the journey. But before that, what is a prime number? The number that gives you only one window, or two if you consider the sleeping and the waking one. You see how we break down these ideas and we use a problem, because at the beginning when you started, you didn't know how to do it. You just had to figure it out. We use a problem to cover curriculum, to cover standards. Yes? In this case, area, perimeter, factors, prime numbers, all of those are lines in your standards in New Jersey. So this shouldn't be an activity that is isolated. These kind of activities can navigate you through the whole school year, and they should. All right. Give you another thinking question, and then we move on. Consider a rectangle, such as this one. Do you see it? What would happen to its area if one of its dimensions were increased by a 10% and the other was decreased by a 10%? Now, before we jump into the numbers, I want you to raise your hand with your intuition. Raise your left hand if you think that the area would change. Raise your right hand if you think that it compensates. I'm going to say 3, 2, 1. You raise your left hand if you think that the new area will be different. You raise your right hand if you think that it compensates. 1, 2, 3. Some lefts, some rights. This is beautiful. When there is a discrepancy or a debate in the classroom. If not, you take the role of being against everyone else. If all the kids think A, you think B, automatically. So that they have to defend their position. So now here we have some people who rose their right arm and people who rose their left arm. And therefore, if we had more time, we could open a conversation. What makes you think this? Try to convince him or try to convince her. Last year, I asked the kid, that was at your school, I think, that I asked, what was it, second grade, I think, or fourth? Maybe second or fourth. I was asking them, can you convince your partner? And he was like, no, Mr. Albert, that's rude. Like, no, it's not rude. Let's just, maybe I didn't express myself properly, but I didn't want you to condition or force the other one to think like you. It's just a matter of a healthy debate and try to convince your partner. It's not rude if you're polite and if you use mathematical argumentation. So here, ideas. What could we do to figure this out? Some ideas.
So we made a 10 by 10.
Okay, so first idea is try, pose yourself an example, and investigate. And
then we get 11 and 9, which is 99, so it does change.
So 10 times 10 would be, why did you choose 10?
Because it's
Just easier.
10%. So
10% is much easier. If you choose 25, good luck, right? Because you then need halves of a square. So that I see a lot. Of course, this is a fake class. You're not students, but I would see a lot in this group with their choice of choosing a 10 times 10. They are understanding what makes it easier. They are understanding that 10% is related to number 10 much easier than to other numbers or to 100. So Is this enough of a proof to see that when you change these, the area decreases?
Like if you did 4 and 5, you're down to 3.6 and 4.5.
So could we choose lengths that allow your investigation to be easy with a rectangle similar to the 10 and 10? Maybe we could
20.
take 20 and 10. Let's try that. Imagine a rectangle that is 10 times 20. What's the area? 200. Now we have 11 and 19. What's the area? Good luck with 19 times 11. 209. So it's smaller compared to the previous one, which was 210. It's smaller again. So apparently, when we do this, it doesn't matter if it's a square of a rectangle, but I love this conversation. And you are following exactly the same line of thought that I was following when I first time did this activity, which was, at the beginning, I thought it compensates. Then I thought, let's try with a square. Then I thought, well, it doesn't compensate. It's less. But then I thought, well, but maybe because it's a square. And then I thought, let's try with a rectangle. And then I saw, oh, still the same. Same thought process. And now I could navigate this, and I was very lucky as a teacher because you were just following my line of thought. If not, of course, you have to add your magic, and we all know this very well. You want to see a proof just for, I would say, 8th grade? This is the proof. But if I was in 3rd, 4th, or 5th grade, I would be happy with this conversation and this investigation and conclude that it gets smaller and that's it. But what is the proof? Just for you to see it. It's a beautiful, super easy to follow proof. Given the area, A times B. Yes? Stay with me. A times B. Lock the doors because we're dealing with letters and some people panic. Don't worry. It's just a moment. It won't hurt. A times B. A is the base and B is the height. Okay? The new area is 0.9 times A times 1.1 times B. Do you agree? That's a minus 10% and a plus 10%. Yes? So we rearrange these numbers and we see that the new area is 0.99, the former area. So it's always going to be a 99% of the previous area, no matter what A and B are, a rectangle or a square. Yes? Imagine kids that have been thinking about this problem in 3rd, in 4th, to deal with area without algebra. And then later on, a teacher says, hey, remember that problem? Let's do it again with numbers. And then, could we generalize this? Isn't this giving much more purpose to algebra and the letters and the use of symbols? Rather than just coming into class and say, hey, kids, today we're going to change numbers for letters. And I promise you, coming from high school background and middle school, that is the day half of the class disconnects. The moment you change letters for numbers. Why? Because everything you learned as like a memory thing, like a recipe, follow steps, the moment I change the ingredients, everything falls apart, right? So there is a good activity to deal with this. And I think we don't have time for this one, so I'm going to move on. I'm 100% with what Dr. Milou said about these posters that you have in many classes in the States. Spanish classrooms are much more boring. Sometimes that is better, sometimes that is worse, I give you that. But the walls of a Spanish classroom, even in elementary, are empty. We don't have a ton of posters. When first time I came into an American school and went into a classroom for the first time out of the movies, I was like, where is the teacher? I mean, I'm overwhelmed with a ton of sugar sentences, right? And some of them are good, yes, but some of them are just hanging there to think, okay, I already taught this, they have this there, but then what, right? Is that enough? How are we connecting this? So honestly, I don't really enjoy these lists of steps to solve problems, but as a teacher, you should know that this is what makes like a good problem and what makes the 4 phases to solve it. First, understand it. And that might mean just read it, but sometimes it might mean draw it, and sometimes you don't need a drawing, but you need like to do some proofs. Yes, that's trying to understand, figure out the problem. I don't know if that's your experience, but I've been now 2.5 years visiting American schools, and I think that you have a similar problem that what we have in Spain or in Latin America, which is kids don't understand what they read. And that's a blocker number one. If they don't understand what they read, the rest of steps are meaningless, right? So we need to devote more and more attention to this. 2, design and execute a plan. Sometimes this design will be as easy as just trying. Sometimes you really need to think about the steps. 3, reflect. And I love these questions. Check your answers, ask questions like, does this make sense? It's just, sometimes haven't you heard, especially the older grades when they do an algorithm and, oh, but I just made a mistake and I moved the comma or the dot. No. That's not an excuse. You're not even thinking on what this number means, because you're telling me that every kid got 250 cookies when at the beginning we only had 25 cookies. So are you making sense of what you're doing? That's the end of the problem. And number 4, sometimes it's hard, but it's what I tried to model with the Windows problem, is go beyond the original question. Pose yourself new questions. Guide your own investigation. The older the kids, the easier this number 4 is. And there, my favorite question is, what if? What if the price was different? What if instead of rectangular windows, we had any shape, like the Tetris pieces, right? What would change? How that would change? We always say at Innovament that activities are like trees. You have the trunk, what you want to do for sure, and then you have branches, many branches. You could explore them or not. You don't have time to go to all of them, but knowing and seeing the tree means that you are, as a teacher, able to explore one branch and maybe leave another branch for later or for another day, right? And explore it in a way that kids are navigated by their interest. And sometimes a context like the Beatles and Britney Spears or Taylor Swift is good, but sometimes just a math investigation like the one we did is also good enough. Okay, so these are the 4 steps, and with that, I think we removed the second pebble in our shoe. We're gonna go for the 3rd one, okay? We're good? How are your shoes feeling? Yes? A little lighter? 3, the mathematical horizon. As teachers, we should keep an eye, maintain, have awareness of the landscape or mathematical horizon to effectively guide students' learning. This is a quote from 1993, Deborah Ball, a wonderful article that dives into what a math teacher should know. Even before the grade you're teaching and after the grade you're teaching, you need to have a broader perspective. So if you feel like me, after a few years teaching the same grades, that your scope is narrowing, try to open it again. Have a conversation with another grade teacher. Read something from another grade. Try to do an activity on your own from another grade. Try to refresh your mindset. What is this? What do you think this is for, or what do you think this represents? Okay, it's some sort of a number line. Yes, it's a line and it has numbers, so I agree. Yes. What else? Counting. We can count here, back and forth, yes. Do you think the colors are randomly picked? No, why not? Multiples of 5, why? To help the kids make 5s and 10s, yes. Okay. And you guessed right, we're going to the number line, but this is like a proto number line, an earlier number line, right? Actually, oh, thank you, I didn't see that. So, actually, I love that you're showing this, because coming from high school, again, one of my first mistakes as a teacher was thinking in kinder, this is the same as that. Hey, no. This is physical, you can touch it. This is not physical, you cannot touch it. So thinking as an adult, oh yeah, it's the same, it's just a representation. No. One thing is a picture of a tree, and another thing is a physical tree that you can touch. And when you're a kid, when you're starting, thank you, when you're starting, it makes a huge difference, right? So don't get me wrong, we would start with the physical one and move to this one. Is this helping us with counting? Yes. Is this helping us with addition and subtraction? Yes. Where do you think we're going? This is the beginning. What's in our horizon? Brainstorm ideas. Where are we going with this? Just don't be scared. Any thing that you see in the horizon is worth mentioning. Where are we going? Yes?
With this, we're working within 20, and eventually they're going to be working within 100, and then 1,000, and then...
Okay, so when you look at the horizon, you see an extension of this number line. Indeed, there is a moment in which we go beyond the 20, and we go to 50, and then 100. What else? Do you think that we will keep, or I would be happy with a fourth grader using these to count? We need to move on, right?
To a number line, which is just like...
To a number line, right? First with the numbers like in a ruler, and eventually, not even that, right? An empty number line, the famous empty number line, right? Many teachers tell us, and it's not that common in the US because you're very much aware of the number line and it's in your standards in New Jersey, but many teachers, especially when we started back in Spain, were not aware of the number line, and they were like, oh yes, these guys from Innova, they just love the number line. But it's not just us. This is a fundamental model to imagine and envision numbers and infinite numbers. So after we discover the empty number line, what can we introduce to kids thanks to the empty number line? Fractions, thank you. And that is about these little lies that we tell as teachers, pretty little lies to the kids. What's after 1, 2? Hey, excuse me? You have an infinite amount of numbers between 1 and 2, but you're not ready to learn that. So I'm going to tell you that after 1, the next one is 2. And it's some sort of a true when you're in the natural numbers world. But then how can imagine that you're not dealing with a number line, the empty number line. How can I deal with fractions and explaining a kid fractions if the kid has only been counting with wholes, right, and beats? You have to cut a bit in half, and that's a difficult understanding. On the other hand, when you have the empty number line, it's much easier to locate fractions. What else? Negative numbers. Another lie. What's the first number? 0. Guess what? You have an infinite amount of numbers to the other side of the 0, right? So that's another idea. When we started today, I showed you a a line graph. Was that somehow related to a number line? It's 2 number lines. So the moment you have to explain graphs, you're now looking at the food and not at me. I get it. How many? How did you count? You can think. Okay, so all this is in your horizon. And I know here probably the audience is a privileged audience. You have the time and the consciousness to come to these kind of events and talk about math education. But what about the rest of the teachers, right? What about, do they know what's in their mathematical horizon? Do they come to you asking, why are we teaching this now? Because that is an annoying question, but it's an important one that we should address. They should know where we're going. So let me show you. Oh, this is a nightmare of a session. If you're a first-grade teacher using InnovaMath, this session is a nightmare. Why it's a nightmare? We always get complaints every year. Imelda is laughing because she suffers many of them. Because many kids already know how to add 8 plus 7. They know it's 15. So when you ask them to decompose the 7 into 2 and 5, why? You see where I'm going? Connected to the 42 that we were doing at the beginning. If you break the 7 in 2 and 5, then the 8 can jump to 10 and then 5 more. And kids are really annoyed when you ask them to do this if they already know the 8 plus 7. But what we're doing here, trying to force the kids a little bit to do this even though they don't need it, a few of them don't need it, it's because later on, these kind of strategies of breaking numbers will be beneficial, right? So even though you don't need this now, it's an investment. This is another picture of our horizon, right? You see, indicate which representation is easiest for you to subtract 43 minus 18 and use it to perform the subtraction, giving the kids the agency to choose what strategy works better for them. Fractions, you already said that. How can this is from later on, how can I explain fractions, whole numbers, mixed numbers without the number line? Oh, and I love this one. It says, it's very small, I'm reading for you. Jump from 0 to 28 in 3 different ways by making jumps using whole numbers of the same length. What are we doing here? Give me a way of jumping from 0 to 28 in jumps of equal length. Give me one way. 4 jumps of 7. Would that work? Okay. Another one. 7 jumps of 4.
One jump of 28.
1 jump of 28. Oh, the other day there was this kid that told me, Mr. Albert, I always do just 1 jump. And I'm like, okay, how do I get rid of this thought for that kid? So you see me drawing a number line on the ground and saying, okay, I'm gonna jump 100 in 1 jump. And I jump and I almost fall, and it's like I'm kind of a clown when I'm teaching. So all the kids like, wow, wow. And I'm saying, what's your conclusion? And then magically, I was lucky, a kid says that sometimes if you do just 1 jump, you fall. Thank you. Yes, sometimes it's better to break it, right? What are we dealing with here? The number line is a useful tool to teach what? Fractions, but here in this particular, factors, sorry. Okay, factors, yes? All the different ways in which you can jump in whole numbers of the same length are the factors of a number. You see that how this connects to the windows? It's another way of seeing factors, right? If you only can make 1 jump, then it's a prime number. Yes? Okay, and you also guessed this well, negative numbers. Yes? Okay, I had this activity, but I think I prefer to finish with another one, so I'm gonna leave it here and let you read it for a second, and then you can practice if you want later, or take a picture and think about it. It's a 7th grade activity, so it's a little, because it's with negative numbers, but it says, choose a starting number and start jumping towards 0, sticking to the following rule. The first jump is 1 unit. Each jump needs to be 1 unit longer than the last, and the priority is jumping towards 0, but if you land on a number you have already visited, you have to go the other way. Feels confusing the first time, but then you can show an example. Since we will be sharing the slides with you, you can check later, okay? So you keep jumping. Starting at 9, the path would be this one. What numbers did you visit? And you can talk about negative numbers. This was just to show you how we organize math. This is, I don't pretend that you see this. This is, Peter Liljedahl calls this the Excel of doom. Because when we showed this to him, he was like, this is overwhelming. Yes, it is. But it's all the trajectories of math learning, all the contents beyond the Common Core, any country, all put there, and try to link where we're going with each of the things that we're teaching to the kids, right? So the number line, you could find the number line trend here, and you would see the beads necklace at the beginning of the journey and the jumps with negative numbers at the end of the journey, and the axes of coordinates, etc. And that gives us horizon, right, as math teachers, and that's why PD is so important. So 3rd pebble out of our shoe, I shoot at the number 5 pebble, which is time management, which is number 1 weakness for me, always. And let's talk about the teacher's role for a second. Memorize this list of numbers. Good? No. Absolutely not, of course. This, what you experience right now, this feeling of, come on. This is what many of your kids, not maybe your kids, but many of the kids in front of a teacher in math are experiencing. Come on, how do you mean that I need to memorize all these times tables by Monday, right? How do you mean this? So let me show you this infographics. It's a mountain, the mountain of knowledge, if you may call it. And there's 2 approaches. One approach is the green one, is the teacher that takes the kids, of course as a guide, and navigates them, crosses the river, and you go milestone by milestone. You sometimes go back a little bit because you need to then 1 step back to do 2 more forward. And it's a long but enjoyable journey. And then on the right side, you have the helicopter teacher, which says, okay, kids, just jump here, learn this, memorize it, don't ask questions, move on, stay testing at the head. Done, next year, right? The biggest idea here, and sometimes we have to take some shortcuts and get in the helicopter. I'm the first one doing this sometimes. But in general, don't be a helicopter teacher, right? Try not to be a helicopter teacher. So we're going to finish trying to avoid the helicopter to teach you the times 17 table. We have around 5-ish, 10 minutes. And we're going to try to do this before we go to have lunch, okay? So I need, really quick, 11 volunteers to come here with a whiteboard. I need 11. The more you doubt, the less time we have to lunch. Thank you. The first one, I need 11 volunteers. Thank you, thank you. Come, come, come.
I'm here to support. We have
11 volunteers with a whiteboard. Okay.
4, 5.
How many? How many?
6, 7, 8.
Thank you, thank you, thank you.
Nobody wants
How
to
many?
do 17 times?
You can use this side. Yeah, don't worry. How many? How many? I'm not counting them. You count them. How many?
I heard we have a very easy person back here that wasn't in 17 times.
How many do you see? It's 10. Are we happy? Thank you, Lisa. Yes. Thank you, thank you. Okay, do you know by heart the times 17 table? No? You promise me you don't? Okay, if you do, be quiet. It's cheating. Okay? Okay, now I could come to the class and say, hey, okay, kids, how much time do you need to read the times this 17 table? Just 30 seconds. That's it, move on, remember it by Monday. Is that working? How many times do you teach fractions? 3rd grade, 4th grade, 5th grade, 7th grade, 11th grade? You teach fraction 1,000 times because every time it's like starting over. Why? Because it feels disconnected from the rest of the knowledge. So we're gonna try to connect the times 17 tables with the rest of the knowledge that we have. Okay, is there any result of the times table that you already know? As we think, can you write 17 times 0, times 1, times 2? Not the answer, just the equation. 17 times 3, 17 times 4, not the answer, just the equation. Okay? So it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And that's off. Yes? Okay. Is there any of these results that you feel confident with? That we already memorized? Oh, so you know some results of the times 17 tables. You cheated. Okay, which ones?
17 times 1.
Okay, 17 times 1, you are the chosen one. Everyone feels so confident about this one, which is 17. Can you write a 17?
Like a flashcard or like a...
A flashcard is all right. Yeah, you can. It's all right. 17. Anything else that we already know? Times?
0.
Times 10. We all know that one as well. So at least we know 2 results of the times 17 table. What else? Okay, she was like feeling, why are you bullying me? Everyone knows this one. Okay, which is? 0. Is 0. Okay, so 0, 17, and 117. Okay, now, let's see. We probably can, I mean, there's a problem with 17 times 2. Probably you know it, but doubling 17, doesn't feel like easy, very, very easy. What about 17 times 5? Could we use something that we know? Can we halve 170 like that? What is it? 85? Can we have 85 here, there? Do we agree? Half of 170? Easy enough, right? Okay, we could subtract 17 from here. The problem that we have, it's a good one, but the problem that I encounter with the kids is that subtracting 7 from here, yeah, we could do that, but maybe later we have another way that is a little easier. But of course it works. Of course it works. There are many ways. I'm now interested in probably this one. This is going to be a key, right? So what do we do here? Some ideas. We can double that. We can halve that. Okay. 10 and 10, 7 and 7. Is that easy enough? Yeah, 7 and 7 is 14. 10 and 10, right? So 34. Okay, so let's recap. 0, 17, 34. Okay, can we do... Oh, double the double. So can we do 17 times what? 4, which is 34 times 2, which is? 68. Okay, recap. 0, 70. I know you need energies. We're going to have lunch in a second. 0, 17, 34, 68, we're missing this one. What do you prefer? Oh, this is a good one. Add 17 to 34, boo, or subtract 17 from 68. No regrouping.
Yeah.
Yes. Can we subtract from here? And it is?
51.
51. Is 51 a key to anything else? Oh, first goes to 6. Can we double 61 like that? And that's 51. It's 102. Recap. 0,
0,
17.
34,
51, 68, 85, 102.
Okay, we're only missing 3. What do you prefer now? Maybe 17 times 8 or 17 times 9? 17 times 9 feels very easy because 51 is a rather simple number to triplicate, right? What's the triple of 51? 3 groups of 50 and not 3. Are we good with that? So 153. Okay, so now we're only missing 2.
Double the 4.
Okay, double the 4s. Where is the 4? Can we double the 68 easy enough? What is it? 136. Yes? Do you agree?
I wasn't doing it.
Okay. So why is always this guy, the 7, right? Always the same guy, right? So what do we do? What do you prefer? Adding 17 here? Come on, it was easy, right? Or we could do the 5 and the 2. But what do you prefer? The 5 and the 2? What's the 2?
5 was 85.
85 plus 34? Or do you prefer 102 plus 17?
2 and 7.
Then this number is, yes? Okay, so I'm going to do it twice. The first time, they're going to show the numbers. And the second time, we go blind. If we know it, we eat. 7 times 0.
0,
Or I'm going to go the other way around. 0 times 17.
0,
1 times 17.
17,
2 times 17.
34,
3 times 17.
51,
4 times 17.
68,
5 times 17.
85,
6 times 17. 7 times 17.
119,
Yeah.
136,
8 times 17, 136. 9 times 17.
153,
And 10 times 17.
170.
Okay, hide them. We're not using, oh, you can show your equation, but not the result. 17 times 0. 1 times 17.
17,
2 times 17.
34,
3 times 17.
51,
51, remember the 51 is a key. 4 times 17.
68,
68, yeah. 5 times 17.
85,
85. It ends in 5. It's the only one ending in 5. That's a good memory trick. 6 times 17. Yes, 102. Related to the 51. I told you the 51 was a key. 17 times 7 or 7 times 17? 119. Yeah, 17 more. 17 times 8 or 8 times 17?
136,
136. 9 times 17?
153,
153. Remember the 7 with the 3. And last but not least, 10 times 17?
170.
Okay, thank you. As you go back to your seats, a round of applause for our 17 table. Is this magic? If I ask you after lunch, do you remember that? No. But if you don't remember, at least, do you know the way now to remember? That's what we need our kids to be remembering, right? So here we had the results. I promise I'm finishing. Can you memorize these numbers now? A helicopter teacher would have told you, but since I am not a helicopter teacher, I tried to make sense of this, right? So, conclusions. Number 1, everyone is a math person. Pebble out. Number 2, problem solving requires thinking. If you're not thinking, you're not solving anything. It's what you do when you don't know what to do. Number 3, keep an eye on the horizon. Not only where we're going, but also where we're coming from. And 4, be a guide, not a helicopter. Thank you so much, and enjoy the lunch.